Hello. Today we're going to talk about iterated function systems and similarity dimension. When I started reading into this topic, I really thought I'd be more interested in iterated functions, um, the systems of those, and how that all put together. But what ended up becoming more interesting was actually the dimensions of similarity. So we've already seen some of this, so some of it's going to sound very familiar. But this is just going to give a brief introduction to some different ways to measure dimension when you have fractals. So as a review about what iterated functions are, that's what we've been studying all semester. Um, we can have a system of these functions, and we're going to say that S is a closed subset of Rn. It doesn't have to be of Rn. It can just be any compact set, but to make it easier for us to understand, we're going to use real numbers. A mapping M takes S to S is called a contraction on S if there is a number R between 0 and 1 such that applying that mapping to X and Y, you're going to find the distance between that mapping to be less than or equal to the ratio times the original distance. And this is traditional distance that we're used to seeing, which is one reason why using Rn makes sense here, so that we can speak about that distance. From this, it's easy to observe that any contraction is going to be continuous. If you just think about the contractions you learned back in geometry in high school even, those were definitely continuous contractions. And if we consider the situation where they're actually going to be the equivalency, then M transforms these different sets into geometrically similar sets. So this is one thing that we can call self-similar sets. So M is what we call a contracting similarity. It's not just a contracting function, but it's a contracting similarity. The family of all those contractions, so if you take that whole, all of those contractions and put the group of them together, you have to have at least two of them, and that's how we get the iterated function system. It's not just here, let's contract, it's all of those things together. And this should sound similar because we talked about something similar with the Cantor set. So there's this thing called the Hutchinson operator. It was developed actually by Hutchinson in 81 back in Indiana, at Indiana University was where this was published, which I thought was kind of cool, kind of close to home, and fairly recent to our time. It's not super long ago, like so much math, which is one thing that makes this stuff so interesting. A set or family of contractions that we just talked about, we have this whole group of contractions. It's going to be for a compact set X. So you have to have a compact set. And then you're going to take the iterated map, and the map is the iterations from X to X, with the iteration being somewhere between 1 and capital N. So again, it could be 1 in this case. So you could be iterating it just once, which just means you apply the mapping once. So you apply that contraction once. But when we operate on the compact subsets of X, so S being a subset of X, then the Hutchinson operator is the union of all of those mappings. So on the previous slide, we had the mapping that took all the different pieces, all the different sets, and it contracted it and it gave you a new set. Well, this is going to be the union of all of those things together, so that whole group. Then once you have that operator, if you iterate that operator in a recursive definition here, recursively defined, where the next iteration, just plug it back in. since we're doing the iterations on the S, so now I'm changing the actual subset. I'm no longer just looking at the set, but now I'm changing the subset. And if I do that over and over and over again, I do end up having a union of all of these subsets, but this is where we came down into that whole intersection of those unions when we talked about Cantor. The limit of this iteration is what we're going to call the attractor. So this is the attracting set generally, and it's the limit as n goes to infinity of all of those SNs. So all of those subsets, if I find the infinite subset of those, that's where I'm going to get my actual set, which geometrically is usually a fractal. Okay. We, again, talked about that a little bit when we talked about Cantor. Kind of goes back into that. But when we go a little bit further, we can talk about dimensions of those things. Because if you think about it, when you were looking at the Cantor set, for example, we didn't really discuss what the dimension of that would be. We did find out, we did learn that it had no measure, and that it was just a whole bunch of isolated points, that there was no intervals. And I actually should have put that proof in here, but I didn't, and I'm not going to go back now. But we can easily prove actually that the Cantor set has no intervals. It's not a very difficult proof. But that kind of brings up a weird idea of, well, how do you describe it dimensionally? So what does a dimension actually mean? What is the definition of dimension? So a dimension is actually the minimum number of coordinates required to describe every point in the set. And this part stuck out to me. It describes every point in the set. So it's not just how many coordinates do I need to describe the set, but it's every single point in the set has to be described, which makes it a little confusing when you start thinking about, I have an infinite number of points, but I have no measure to it. There's no like thickness to it. There's no bulk. So it doesn't really make sense. It's hard to get your head around what that could actually mean dimension-wise. Well, let's think about some basic ones, okay? Intuitive examples, intuitive things we know. A line segment. A line segment is one dimension, has one dimension. We know that it's one-dimensional because back in Algebra 1 in high school, we learned that if you had y equals 2, for example, then we could picture that as a line going through the y coordinate of 2. It doesn't need an x because it doesn't matter what x is, it's always going to be that. It's always going to be just that straight line. It's one-dimensional. It takes one coordinate to describe that entire set because a line is a set of points. So it takes one coordinate to describe that. Now a square or a plane even, if you want to think more infinity-like, we could talk about an actual plane. And this is going to take two coordinates for us to describe. If I want to describe every single point on this plane, then I could think of it as the coordinate plane x, y. And if I want to describe a point on there, every single point, I'm going to need both x and y. Because if I don't have both x and y, I can't describe, for instance, this point. I could describe that with an x coordinate, or I could describe it with a y coordinate. But if I want to describe where it lays in this plane and I want to describe the entire plane, then I need both coordinates x and y. Now, if I look at the cube, for example, we pretty much know, we should know, that a cube is going to be 3 dimensions. So this was when your calculus professor kind of blew your mind when they were able to draw this crazy looking thing here and gave you a three-dimensional graph for the very first time. Well, for me it was calculus, but I also didn't pay attention in high school math. So that was for me, was calculus when I first saw the three-dimensional graph here. So we had an x, a y. We have a, hold on, see if I can remember to do this correctly. There's the x, there's the y, and there's the z. That's the way I'm going to align it. Doesn't really matter. You can do it any way you want. You define which one's which. X, Y, and Z are kind of just our way of describing it, but you can use anything else that if you wanted, of course, we all know that. But this would be our three-dimensional graph. In order to define this cube, I would have to have all three dimensions. You'd have to have the length, the width, and the height. So you'd need to have all three dimensions in order to define the cube. Okay, that's great. Why do I care? Well, it's a little counterintuitive to try and think about the dimensions of the middle thirds Cantor set or the von Koch curve. So the one we already talked about, the middle thirds Cantor, where you're really talking about a whole bunch of points. But a point has no dimension. So that's a little weird and hard to understand. But it's also not just a point. There's a lot more to it than just a point. So how are you going to end up describing that in dimensions? The von Koch curve is also a little counterintuitive to understand because you would think, hey, it's a curve. Maybe it's just one dimensional like other curves are, like that line was, the line segment was. But if you think about the line segment as a dimension, what are you actually doing in that definition right there? You're talking about something that has a length, and it has a set length for that segment. Well, the von Koch curve actually doesn't make sense there because it is infinitely long in just that one interval. So when you start breaking it down, when you take this initial point or initial line, you break it into three pieces, and you're going to remove that middle piece, and then you're going to put two pieces in its place. And then you're going to do that same thing, and you're going to take this part here, and you're going to remove this middle piece, and you're going to put two pieces in its place. So when you keep going, you're actually adding another third to every layer. So I added another length of 1/3 in that first iteration there. I had a length of 1, but then I added this other piece here. So I added a length of 1/3. So this is 1 plus 1/3. So the length of this just got bigger by 1/3. And if I keep doing that and keep doing that and keep doing that, then I'm going to add another 1/3 to each part as I go. And it's not going to make any sense when I start getting to, well, what's the measure of this? So I have to find a different way to define the dimension. Not necessarily a different way to define it, but a different way to look at it. So let's look at it a different way. We have something called a similarity dimension. And the similarity dimension, actually, this is tied into the Hausdorff dimension. I think it's called Hausdorff. I always call it Hausdorff, but some people say it different. This is tied into that. The value of S satisfying this equation here, so this exponent that satisfies this equation is going to be the similarity dimension. So that is going to be related to the Hausdorff dimension, and it's the similarity dimension. The similarity dimension is the same as the what's called the box dimension and the Hausdorff dimension. So those two things generally can be explained together in the similarity dimension in most cases. I did read about a couple of examples of when that wouldn't happen, but to be completely honest, I got kind of lost in a lot of that because some of those are really theoretical, not something that you can picture, and that was hard. So how do I actually apply this and how do I find it? Well, the pieces of this are pretty simple to see. The R is the ratio of the contraction. So remember we had um, the measures of this was an X, and then the mapping of the Y measure, and then that was going to be less than or equal to R times X minus Y. This R right here is the ratio of the contraction. So as long as R is between 0 and 1, then this is going to be a contracting map, and we're going to have a similarity dimension because it's going to continue to be able to get smaller and smaller and smaller. The N up here is the number of times that we iterate, which is exactly what it means in the summation. Now, using that, you can get some really interesting results. So using this idea, we can actually determine that the similarity dimension of the middle thirds Cantor set is, so Cantor similarity dimension is actually equal to 2/3, which seems weird. Now, if you think about it, 2/3, it shouldn't be that surprising because you take out the middle third of each of them. So it seems like it should be, but how do you know that? And how can we have a dimension that's not a whole number? How can we have a dimension that's not an integer? That actually isn't all that uncommon. I was surprised to find out. Non-integer dimensions are all over the place. You have 1 dimension, you have 2 dimension, and you have 3 dimension. We already have all those. But the domain of the fractals, the place where fractals live, is in between the integer dimensions. So when you have a fractal, you're going to get a dimension that's somewhere between 1, 2, and 3. You're not going to get, and you might even get something bigger, but that's when things get really weird and complicated and I get confused. Give me another year. Maybe I'll understand it then. But these in between parts here, the domain of the fractal, I like it. That's where you're going to find all those different pieces. And I like how this picture kind of laid it out because it starts with 2 dimensions as being kind of like your initial point. You have that as your starting position. And then it can be scaled down or it can be scaled up. And when you're doing that, things get crazy. They kind of go all over the place. But when you scale it down, it becomes a little bit easier to wrap your head around. It becomes linearized. We all love that term because that's when we can actually do things with it where there's not a whole bunch of noise going on, and it becomes a lot easier to see what's happening. So that's where we generally operate, is between these places here. When you get above that, there are some examples, and we're going to see one in a minute, but things get a lot harder to grab onto. Actually, we're not going to see one of those. We're going to be in this domain here. But it gets crazy. So let's go. Let's look at one. Let's look at actually doing one together. So finding the similarity dimension is akin to solving this equation right here. So this is a simplified version of that summation, which actually made it much, much easier to solve things. So we're solving it for that S, for the exponent. which if you remember our basic algebra, we just apply ln to both sides and we can solve for s. And then here we have an example of the von Koch curve. So I've highlighted the four different versions of this, or no, the four different, four similar pieces. So it's a self-similar curve where we have this piece, then the middle third piece, and then the last third piece. So like we had the example earlier where we had the line and then it went like this and we added these pieces here. So we took that one line, took the middle out, and then we added that other third in. So this is actually going to give us four parts in a ratio, of 1/3. It's actually a ratio of 3 because we always want to think about this guy scaling to like three of them make 3 of the one pieces make one whole. So we're going to scale the ratio to be 3, and then we have 4 iterations of it showing up in that piece, in that 3 pieces. So the m is going to be 4. So 4 iterations in one part broken into 3 pieces. I hope I explained that enough. So then when we just plug these things into our dimension here, we're going to have ln of 4 over ln of 3. And we're going to get that the similarity dimension of the von Koch curve is going to be approximately 1.26, which is between that 1 and 2. It's a little bit closer to 1 dimension, but it's not 1 dimension. And I actually did find that when you look at multiple different fractals, you can see the different ways they relate to the different pieces. So here the von Koch curve is a little bit more complicated than a line segment, but not as complicated as a full plane. The Cantor set is a little bit more complicated than a lot more complicated than just individual points, but not as complicated as a line segment. So it has a dimension of 2/3, which again makes sense because it's between that 0 and 1. Okay, so I have a couple examples of some like practice problems to do. We played with the Cantor set so much that I thought maybe a different version of it might be fun to play with a little bit. There's so many different versions of it. It's all over the place. I actually, in undergrad, did a whole thing about Cantor set and topology and learned quite a bit about it. So this was one way to explore that even deeper, which was really kind of cool. But another version of it is called the even sevenths Cantor set. And I've described how you can do this. I then asked you to find the similarity dimension of that set, which if you think about the way we just broke down, what is the ratio? So how many ratios make the full one? And then how many iterations does it take to fill in that full one? And then if you generalize the construction of that even sevenths, you can come up with pretty much any kind of odd number piece Cantor set. So I know there's an even 11ths Cantor set that I've done a little bit of work with. It's kind of cool. It's kind of cool to see how that works. So play with that and see what you can get out with that. The other one that I thought was cool was just a little bit more abstract. Finding the similarity dimension of the subset closed interval 0 to 1 consisting of real numbers that can be written without the digit 8 appearing anywhere in their decimal expansion. This one took me a little bit, but it was actually pretty cool. And you can get really abstract if you start thinking about just those kinds of things. And For fun, maybe consider what the fractal would look like. What would it look like if you tried to make that into a visual representation? What would the fractal actually look like? Because we're still between the 0 and 3 dimensions. It's still something that we can draw. It's still something that we can actually physically see. So what does it look like? It's kind of interesting. Play with it. Have fun.